In earlier lessons, we learned about system consolidation, the reorganization of memory over time, and we saw the crucial role of the hippocampus in this story, that the hippocampal memory traces will be used to strengthen the cortical memory traces, making long-term memories retrievable without the need of the hippocampus pointer or index. In this lesson, we'll briefly tackle why does the brain bother with this system consolidation? Why reorganize memories in this way? Reason number one, we're going to call the limited storage space in the hippocampus. Now, the hippocampus has relatively fewer synapses compared to the cortex, and this means that newly encoded memories might interfere with older memories within the hippocampus, and system consolidation solves this problem. So if we just think about the number of synapses that are available in the hippocampus compared to the cortex just has a larger capacity to store more information. And so this means then that it makes sense to reorganize memories and get them cortically based rather than keep them in the hippocampus. If memories were stored in the hippocampus, new learning would interfere with older memories because there's a finite number of synapses to play with. Reason number two, we're going to call the synaptic resetting hypothesis of sleep. And this is based on some current research. And the idea is during the day when we're learning things, there's a danger of synaptic saturation in the hippocampus. Remember, there's plasticity, synaptic plasticity occurring amongst hippocampal neurons. Well, there may be some limit to how much plasticity can occur here. So here's the idea. There's a limit to how much LTP can occur at synapses. During wakeful learning, synapses may exhaust their capacity for plasticity. Without resetting hippocampal synapses to a baseline state, the hippocampus would be unable to learn new things. So if we're going to keep the hippocampus in good shape, if we're going to keep it ready to learn new things, we have to weaken these synapses again. So we just can't keep strengthening synapses. There may be a biological limit to how strong they can be. And furthermore, as we learn more and more things, if we just kept strengthening all the hippocampal synapses to their maximum state, then we wouldn't be able to learn anything new. Along comes sleep. And the idea is, let's take a look at the bottom hippocampus here. Here we've got some synapses that were strengthened as a result of the day's learning. Well, that represents newly learned information. Now, system consolidation will reorganize that memory and strengthen the cortical memory traces. And the reason for doing this is because these strengthened synapses have to be weakened again in order to prepare the hippocampus for new learning. So this is one of the functions of sleep. So sleep is going to consolidate the memory in the cortex, but also weaken the hippocampal synapses in preparation for new learning. So again, reason number two then, we've got to reset our hippocampal synapses to prepare the hippocampus for new learning, but then you better have consolidated your recently learned information and get it out of the hippocampus and store it in the cortex, because you don't want to wipe away your memory traces before you consolidate them into the cortex. Reason number three, to get the benefits of neurogenesis. Now, neurogenesis refers to the birth of new neurons. There are very few places in the brain where there's any evidence that new neurons are born, but the hippocampus is one of them. Now, most of this research was done on animals, and it's currently being investigated whether this occurs in humans as well. But the idea is that new neurons being born in the hippocampus have to then take up position and make synaptic connections with older hippocampal neurons. But the problem here is that may interfere and disrupt older memory traces. So, researchers hypothesize that as new neurons integrate into already established neural networks, they interfere with prior memories. Thus, consolidating memories in the cortex would protect the memories from decay. The benefit of new neurons is that they are more plastic, that is, better able to make the synaptic changes necessary for learning and memory. So here we have our hippocampus and here we have our cortex. And the idea is neurogenesis will have the effect of erasing memories in the hippocampus as new neurons take up positions and kind of mess up the memory traces from older information. But as well, researchers suspect that neurogenesis triggers system consolidation, which is going to save the memories. So in other words, there's two complementary roles here. So like with sleep, the effects of neurogenesis are complementary. On the one hand, it may trigger memory preservation, that's the consolidation process. On the other hand, it causes memory erasure. So again then, why do system consolidation? Well, we've got in the hippocampus interference due to new learning, interference due to new neurons, and interference due to synaptic resetting during sleep. So basically, hippocampal memory traces are vulnerable to decay in ways that the cortical memory traces are not. And so it makes sense for the brain then to reorganize memories, to get them cortically based in order to keep that hippocampus fresh, young, ready to learn new things. And so we can say we consolidate what we have already learned so we can be ready to learn some more.